Do you want me to start?
Well, it's a great pleasure for me to introduce my good friend and former office mate, Trebst. And today he's going to be talking about Kitaev materials. And again, as usual, feel free to interrupt at any time, raise your hand, post the question in the chat, or unmute yourself. Otherwise, we'll have time for questions at the end of the talk. All right, Simon, please go ahead.
Yeah, thanks, Adrian, for hosting me for this transatlantic remote seminar. I feel that I might be in a more comfortable position than you are. You know, in my place, it's 9 p.m. and I'm in my institute, so there will be no disturbance while you're, 3 p.m. You know, you sit on your couch, probably your kids are back from school. You know, more challenging for you than me. So I will be talking about Kitaev materials and field-driven phenomena. But before I start doing that, let me start with a very basic question. You know, if I manage to go to the next screen, when do interesting things happen in condensed matter physics? And I think I figured that out. Yeah. So here's a theme, that replays itself in many different situations. So if you're in condensed matter physics and we look for quantum matter, we are typically looking at interacting many body systems. So we take many different degrees of freedom. We have them interact, and things become interesting if the interactions in that system give rise to accidental degeneracies. So if you look at the energy spectrum, for some reason, there's many different states, that satisfy these different interactions in the system in a similar way, and they're all very close by, and populate the ground state. So in such situations, very small residual effects, that typically, we think as, afterthoughts, become very important and can actually split the degeneracy and give you a collective many-body state that you will actually see as the sole ground state. So that sounds very abstract. So when do we encounter such a situation? Well, for instance, in situations where you see phase diagrams that are very complex, So this phase diagram of the coupled superconductors is a classic example of that. You have two parameters that can vary, whole doping and temperature, but if you do so, there's 5 different phases in your phase diagram, And the reason for that is, that below this superconducting dome, most likely a quantum critical point, hides at which, all these phases collapse onto one another. And then, going out of that quantum critical point in different directions, you see, these different phases. And that already, gives us a hint, why this might be also very difficult to describe, what we do here. Those interactions that give rise to that accidental degeneracy. Oh, I should explain what accidental means. Accidental means, there's no underlying symmetry, that enforces, a degeneracy of states. So there is no good reason for that degeneracy to actually survive. Exactly those residual effects that I mentioned. So there's a split of energy scales, that give rise to the degeneracy, and that splits the degeneracy. And these multi-scale problems are always very hard. It comes down to strong coupling. Sometimes we have macroscopic entanglement in these systems, and that makes it hard, but at the same time also very interesting. So let me give you 3 principal examples of this theme, and then dive into the actual topic of the talk. The classical example of this theme is a frustrated magnet. So you take a magnet and you put it on a geometrically frustrated lattice that won't allow for the formation of a conventional Niel state. And the effect of that is that you see in the susceptibility a Curie-Weiss behavior that survives all the way down to very, very low temperatures, way below the actual Curie-Weiss temperature. And the reason for that is that at 0 temperature, there's a huge degeneracy of states that equally well satisfy the constraints coming from the lattice. Some small interaction will then give rise to long-range interaction to long-range order by splitting the degeneracy, and actually makes a system order. And this discrepancy between the actual ordering temperature and the Curie-Weiss temperature is what you often use to characterize how frustrated a system is. So frustrated magnets are a prime example of this theme. Quantum Hall states are another example of that theme. Yeah? So you have interactions. You have electrons in a magnetic field. What you get is Landau levels, which are well spaced from one another. Yeah, that's the simple case. But if you fractionally partially fill such a Landau level, yeah, then there is many different ways of actually doing that. Yeah, so you have a multitude of states that you can occupy, but you only have a fraction of electrons to put into these states. Yeah, and this partial filling gives rise to a huge degeneracy, and then the Coulomb repulsion between the electrons is actually what splits that degeneracy and gives rise to the fraction quantum Hall liquid, which is a topological state of matter, so a super interesting state. And the last example that I want to mention is, of course, something that you have all heard in the last years, is twisted bilayer graphene, where the twisting between the two graphene sheets, at the right angle, generates this flat band. A flat band is nothing but a huge degeneracy of states. There's no dispersion in the system. So all the states have equal energy, and this degeneracy is very quickly split. And if you look at Timo Hefetov's example of a phase diagram here, you see that there is a gazillion different interesting states that pop up out of this flat band. Yeah. So it's a third example of how an accidental degeneracy, in this case by going to a particular angle that has no symmetry associated with it, gives a degeneracy that you then split. So let's look at another example of this physics, but now go to spin orbit materials. That shall be our playground, where we look for this. So all of you have some idea what a material is. Let me explain spin orbit. For those of you who haven't thought about spin orbit coupled materials a lot in the last time. So spin orbit coupling, here, you learn in quantum mechanics, works like this, yeah. So you have, a relativistic correction that tells you, that there is spin orbit coupling. You can immediately understand this, the electron, quickly circling around the nucleus by making a change of reference frame. Let's put, the electron at rest and have the nucleus, go around the electron. If you do that, you realize, that, the positively charged nucleus will create, because it's a charge that moves, will create a magnetic field, at the location of the electron. So the electron spin, will couple, to the magnetic field created by that charge, orbiting around it. And that's precisely, the spin orbit coupling, this L.S coupling between, the angular momentum and the spin. And, in this very crude, picture, where there's a big nucleus and a single electron, you can calculate the spin orbit coupling, so the prefactor in this coupling. And if you do that in this simple, approximation which neglects screening effects by other electrons, you would come to the conclusion that the spin orbit coupling, grows, with the forced power of the atomic number z. Yeah? And let's stick to that very crude estimate, and get an idea of how spin orbit coupling actually changes, as you go through the periodic table. Yeah. So here's the periodic table as a as a single line. All the atoms line up in by their atomic number. And let's put a 1 in this scheme here. When we talk about the cuprates. Yeah. So classical materials. Yeah. And then compare spin orbit coupling in the cuprates to materials over here like iridates or bismuth, where the spin orbit coupling is 1 to 2 orders of magnitude larger. And actually, the effect of spin orbit coupling is then very different, in these different regimes in the periodic table. Yeah. So if you go to the lightest elements, you know that spin orbit coupling is so weak, that it gives rise to an atomic fine structure, and that's something for atomic physicists, to look at. In this intermediate range, when you talk about 3D materials, yeah, so like the cuprates, spin orbit coupling is very moderate, and typically what it does is, it induces a Janoshinsky-Maria interaction that competes with the magnetic exchange in these systems. Yeah? So, you get spin spirals induced by, this Janoshinsky-Maria, which gives rise to multiferroics, for instance. Yeah. When you go, in the regime of the 5D elements, so, deep down in the periodic table, then spin-orbit coupling becomes so large that it actually directly competes with the Hubbard physics of your system. Yeah. So this is a regime, where topological insulators are born, where band inversion effects, make a trivial band insulator into a topological Mott insulator. And this is also the regime where spin-orbit assisted Mott physics plays out. Yeah. And that's, it's actually what we want to look at. Yeah? So, Leon and collaborators a couple of years back wrote a very nice review where they, made this schematic plot where they, compare Hubbard physics to spin-orbit coupling and map out the different regimes, of what might be happening. If you go to the regime where everything is small, spin-orbit coupling is small and correlations are small, then we are in the world of band theory, tight binding models, where we can distinguish, metals from band insulators, something that you learn in your first solid state theory class. Yeah? And the conventional physics is, you ramp up your correlations and you can go into a Mott insulator. Okay, so a correlation-driven insulator. And what we have then learned, later is, that spin-orbit coupling per se, if you put it into a tight binding version of a weakly coupled system, you can get a topological insulator, or its topological metallic friend, the violet semi-metal. Yeah, so they live down here. And then there is this bluish region up here where both spin-orbit coupling and correlations are both large. Yeah, and this is the regime, where spin-orbit entangled Mott insulators live, and a subset, of that regime, close to these topological insulators. This is where these so-called Kitaev materials will live. So let's learn, how they come about. Yeah. So let's start with, a typical material from, that part of the trace diagram, some iridate. Yeah. So iridium is the core component, the atom that will carry, the magnetism in that system. And it typically comes in the valence of 4+, which means that you have a 5d5 configuration. Yeah. So you have d orbitals, in which you put 5 electrons. Yeah. So d orbitals, live, in some octahedral crystal field, that splits immediately these 5 orbitals into T to G, which have lower energy, and then 2 EG states which are higher. Yeah. So your 5 electrons, they live in this T to G manifold, which is like a spin 1. Yeah. It's like it's 3 different states. Yeah. Okay. So it's like L equals 1. So when you now do spin-orbit coupling, you get L equals 1 coupled to a spin 1/2 of the electron, because so there's 3 guys pointing up, 2 guys pointing down. So there's an effective spin 1/2, of these 5 electrons. You couple a spin 1/2 to orbital momentum 1. Yeah, then you get a 3/2 state and a 1/2 state. The distinction between T to G and the true, L equals 1 state is a minus sign, which arranges, these J 3/2 and J 1/2 states in this way, that the 3/2 state is a lower energy state. So that one is filled, and you get, 1 electron in this J 1/2 manifold. Yeah, and that's actually very important because now you have split your electronic bands in this 3/2 and this 1/2 band. And the Mott lobe of this 1/2 band is, has a considerably smaller bandwidth now. Yeah, and it takes much smaller electronic correlations than you would actually expect, for one of these 5D materials, which are very large atoms, which, greatly overlap, with their neighbors, to actually get a Mott insulator. Yeah? So if you would have asked, someone 10 years ago, probably everyone would have said, that 5D materials are generically metals and not insulators, and not Mott insulators for sure. Yeah. But actually, that can happen. Yeah, if you have strong spin-orbit coupling, that makes this Mott lobe of the J 1/2 state very small. The bandwidth, so that a moderate electronic correlation can actually drive you into an insulator. Yeah. So that's why we call these systems spin-orbit assisted Mott insulators. Okay. So now you might ask, why should I care? Yeah. So why are these systems interesting? Well, and there's 2 general reasons. Some of these systems are extremely similar chemically, from their chemical composition to, the cuprate superconductors. So, there's an intense hunt for superconductivity in these spin-orbit entangled Mott insulators, basically trying to expand, that phase diagram that we have seen in the very beginning of, a cuprate superconductor by an additional axis, which, tells you what happens in the presence of strong spin-orbit coupling. Now this talk, will go more in the second direction, that these systems are very prone to, exhibit spin liquid physics. Yeah? And you would like to understand how that actually works. So far we have understood, that the degree of freedom, the local moment in these Mott insulators is this spin orbit entangled degree of freedom. And actually, by this very nature, the interactions, that exist between, these local moments are very different from a conventional magnet. Yeah? And this is something that Ginyat Kalulin, George Heckley, and Jiri Chalupka have worked out very nicely. So they understood that depending on the way that these iridium atoms or these heavy 5D elements are coupled, whether they are coupled via a single oxygen on the edge of one of these octahedra, or through two coupling passes along the edge of two octahedra, you get very different exchanges. In this case here, the corner sharing version, you get conventional Heisenberg exchange. While in the edge sharing case, the effect of these two exchange passes is that they act like a little interferometer, and there's destructive interference that actually kills off the Heisenberg exchange. And the next best thing, that comes up, are these anisotropic exchanges. So instead of getting a conventional Heisenberg exchange, now you get these, bond-directional exchanges, which can be of, Kitaev form, or what's called, this gamma term, which is even more complicated. Yeah, I will come to, the precise notion of what's actually written here in just a second. Now, this theme can be expanded to other materials, where you pull these octahedra, apart from another, but if the element of these two exchange passes still exist, you still end up with these pretty complicated interactions. So let me explain what those are, and start with the Kitaev interactions. So these interactions, that are written here is Si gamma, Sj gamma. So these are couplings which are bond-directional, meaning that if you're looking at a tri-coordinated bond, you go in these three different directions. You couple either the x, y, or z component of the spins. And that's a very dramatic thing. Yeah? So looking at just one of these coupling, you might say, oh, that looks like an Ising coupling, and we know everything about an Ising model. But actually, these are Heisenberg spins, so they can, in the classical world, if you think about classical spins, they can point on spheres. Already that is actually a very frustrating situation if these three different interactions compete with one another. You want to have those spins point in different orthogonal directions to one another. Yeah, so this guy along the y, this along the x, and this along the z direction. So the guy in the middle has no idea where to point. Yeah, and this effect, that these different interactions give rise to possibilities that are all of the same equivalent level. So here, pointing in one of these principal interactions, that's what we call frustration. And in this case, because it's not coming from the geometry of the lattice, but from the exchange, we call it exchange frustration. And I can show you what the effect of that is by sticking to this classical picture. Yeah. So we are a numerical group. We can run classical Monte Carlo simulations. Yeah. And if you do a classical Monte Carlo simulation for the Heisenberg model on, well, let's put this on a honeycomb lattice, for instance. Yeah. You get data like this. You get in the specific heat a feature that seemingly diverges at some temperature. Yeah. So there's apparently a characteristic temperature where magnetic order sets in. Here in this case on a finite system size. Yeah. If you compare that to the Kitaev model, none of that is actually seen. Yeah. So your specific heat, it's non-zero, so the system does release entropy on the way down to zero temperature, but there's never a diverging feature. Yeah. So this is exactly what I explained in the very beginning. So your system behaves like a paramagnet all the way down to zero temperature. Yeah. So it actually never orders. Yeah. Even in the classical sense. So for the aficionados in the audience, what actually happening is the system goes into a Coulomb phase at this lowest temperature in the classical Kitaev model. Yeah. Okay, so we can see here now how to distinguish interesting spin liquid formation from conventional magnetic ordering. Yeah. So nothing in the specific heat versus a peak in the specific heat. Now we can actually go out and look at these materials, these Kitaev materials, and look at their specific heat. So let's do that. So here's a bunch of them. Sodium iridate, lithium iridate, ruthenium trichloride. Actually, what you see is they all have this bump at this specific heat. So they're all magnetically ordered actually. So they all have a temperature scale, in the 10 to 20 Kelvin range, where their spin orbit entangled moments, form some type of magnetic order. Often it's some type of zigzag order, that forms. So you might say, oh, this is very boring. We actually get order and no spin liquids. Well, there's some other materials like this hydrogen intercalated lithium iridate, which actually does not show this. At the same time, this is a system which is actually very prone to effects of disorder. So that might actually be a different story. What's happening here. So let's ignore that for the time being. So we are stuck with these materials here. So the ones that actually magnetically order at low temperature. So are there no spin liquids? Well, so one scenario is that these systems are actually very close to a spin liquid, but they didn't manage, to actually make it into the spin liquid regime. And here's a schematic picture of, what might happen. So, you might assume that, these materials are described by a Kitaev model, the one that gives rise to a spin liquid, but there are some additional couplings. And these additional couplings, they drive you into a magnetically ordered state. And apparently what your experimental system does, it sits in such an magnetically ordered state. So here on the right is spin liquid land, which we missed. Here on the left is magnetically ordered states. But as you go to high temperatures or equivalently to high energies, you might actually see some of the spin liquid physics, just above the magnetic ordering transition. So why is that? That's a free energy argument. So if you go to finer temperatures, you know that you are supposed to look at the free energy instead of the energy. Well, the free energy of a magnetically ordered state is boring. So there's no entropy to be gained in the magnetically ordered state. While a spin liquid, generically has all these different states, around it. So there's a lot of entropy involved. So generically, the magnetically ordered state will bend to the left. So the spin liquid will always win at finite temperature. So there is a chance, that as you crank up temperature, you will actually see, some of the spin liquid physics just above, the magnetic order transition. So my experimental colleagues here in Cologne actually argue that they see that, for instance, in sodium iridate, where they see in their Rix spectrum a broad feature, a continuum of states, that is very reminiscent of, for instance, spinons. Well, here in the Kitaev system, it's slightly different. That survives all the way from some 20 Kelvin all the way up to 300 Kelvin. So it's always there, above the magnetic ordering condition, and it's almost totally ignorant about temperature. Also, if you look at the way that the spectral weight in Rix builds up, it's very reminiscent of what we actually expect for a Kitaev system, which has this two-peak structure in a specific heat, where you have a magnetic ordering condition very low, and then a crossover at very high temperatures, and which comes from the build-up of spin-spin correlations, and these guys almost ideally map out this data. Well, but let's not stick to proximate spin liquids. We want the real data.
Ramon, can I ask you a question on that phase diagram before you go on? If you go back to the previous one. So what is the difference between a Kitaev spin liquid and a disordered Kitaev spin liquid?
Oh, so that's, so these two regimes here, corresponds to, what's happening below this temperature and below that temperature. So the Kitaev model, which I will explain in a second, has two things that happen. So the first thing is that the spin actually fractionalizes into new emergent degrees of freedom, which we will hear about in a second as Majorana fermions and a gauge field. And this fractionalization, that happened at this upper temperature. But the gauge field that actually doesn't order. And this disordered refers to that. So the gauge field is still totally disordered. And it will only order at this lower temperature, which is actually this is a logarithmic plot. Yeah, so it's very, very low, the temperature where the gauge field actually orders. Yeah, and because it's a Z2 gauge field, you will actually see that as a true transition. Yeah.
Okay, so is this phase diagram numerically established, or is this a guess from these experiments?
So this is what's drawn, what is numerically established is, the phase diagram on this line. That's what you see here. Okay. Yeah, so that's actually Monte Carlo results. Yeah, in this in the pure Kitaev limit, there's no sign problem, and you can solve this. Yeah? This direction here, we will do in a different way. We will use exactization, and you will see plots of that. Later in the talk, for a different parameter, it will be a magnetic field, but you will see how we are able to, trace, these two transitions. Yeah, way above, beyond the exactly solvable regime. Okay, so yeah, okay, and it does look like this. But this is actually a schematic plot. Yeah, so I drew this in whatever I'm using here, Keynote.
Okay, great, thank you.
Good. So that's a story about proximate spin liquid. What we want to do is a real thing. Yeah. So the real spin liquid, and there might be a good chance to actually see this in the material that's called ruthenium trichloride. Yeah. So which is a 4D material, and which, when you put it in a magnetic field, also has the effect of destroying the magnetic order that you get in the absence of a magnetic field. Yeah. So this transition to some zigzag order, that happens, around 8 Kelvin here. Yeah, that disappears when you crank up a magnetic field. So that's good. Yeah. So a magnetic field can also destroy, the magnetic order. And the question is, whether something interesting happens, before you fully polarize your system, which will eventually happen for large magnetic fields. And the interesting observation that has been done is the one that is highlighted here down here in experiments in Kyoto. Kasahara and Matsuda have observed a thermal Hall effect, yeah, an half integer quantized thermal Hall effect, yeah, which is a revolutionary experiment. So there's a full slide for that. Yeah, so they say that in a regime, yeah, in magnetic field ranges, beyond that magnetic ordering disappearing, and before the system goes into trivial polarized states, there is a regime where they can observe a quantized thermal Hall effect. So what is that? Yeah? So this material is almost two-dimensional. They put it into a magnetic field. Yeah, that's the one that destroys the magnetic order. Yeah, and then they make one side of the sample hot and the other one cold. So there's a temperature gradient, and then they actually see that there is a transverse Hall effect. Yeah, so you see that the system acts with heat in the same way that we know from the electronic Hall effect. Yeah? So, and they get this quantization, which is half quantized. Yeah. So first of all, they get the quantization. Yeah. So that's pretty cool already. Yeah. So here's a plateau, that you're supposed to see here. Yeah. Which is for some field range, different temperatures, and different angles of the magnetic field with respect to the plane. Yeah. And the half quantization tells you that what actually carries the heat in the system, yeah, is not an electron. Yeah, so it's half an electron, yeah? And this half electron we will get to know in a second as a Majorana fermion. Yeah, so the half quantization is direct evidence for fractionalization in this system, and this Majorana fermion that we will discuss in just a second. Yeah, you should also note that the thermal Hall effect occurs at temperatures that are pretty high. Yeah, so it's 5 Kelvin down to slightly below 4 Kelvin. So we don't have to go to ultra low temperatures to observe this. We will also come back to that point in a bit. So let me try to explain some of the physics that's going on here by giving you a more systematic introduction to quantum Kitaev spin liquids and their magnetic field effects. And I should say that this is work that I've done together with my postdoc Kieran Hickey. He did it together with me. So Alexei Kitaev solved this model, yeah, where you have these bond-directional interactions, and many of you have heard how this is done. Yeah. So the genuine trick, yeah, is to actually decompose the spin degrees of freedom in parton degrees of freedom. You know, these partons are Majorana fermions. Yeah. So you write every spin operator in terms of 2 Majorana fermion operators, and then because you have 3 different spin operators, you have a couple of different Majorana operators. Actually, you have 4 different ones, yeah, which you can arrange in this way. Yeah. So for the different couplings, there is 1 plus 1 for each side. Yeah. Okay, so we're using Majorana fermions, and already at this point, you can deduct, you know, the most important thing that I want you to learn, and that is, well, you can say, well, this spin representation I can actually change. I can add a phase, yeah, you know, to this parton operator, you know, this Majorana operator, yeah, and if I do this, you know, in a clever way, you know, because I have 2 operators, you know, I can add a phase, I can, you know, subtract it again, and the spin operator doesn't change. Okay, so, and this will tell us something, because the next step we have to, you know, take into account is the idea that these operators that we're dealing with are Majorana fermion operators. So the Majorana fermion, you know, that's its own antiparticle. So C squared is 1, yeah, but actually that constrains this phase, yeah. It means, you know, that if you square this operator, you know, you have to go back to 1. So this phase can only be, you know, plus or minus pi, yeah. So you know, 0 pi. That's what I want to say. Yeah, so there's a Z2 redundancy in this entire construction, you know, built in. And actually, that's the only thing that I want you to sort of keep in mind for now. You know, this representation, you know, very naturally, you know, leads you to the notion that, you know, the gauge structure, yeah, that is associated with, you know, this physics here is a Z2 gauge structure. Yeah, so the Kitaev spin liquid is a textbook example of a Z2 spin liquid. Meaning that at the end of the day, you know, your spins decompose. Yeah, you have a free Majorana fermion, that's this yellow guy here. Yeah, you know, hopping in a Z2 gauge background. So you have a lattice gauge theory, you know, with a Z2 gauge field, and you have these Majorana fermions hopping in it. And this is really textbook knowledge now. Yeah, so, you know, many of you, you know, might have heard this, you know, during, you know, your solid state theory courses. Yeah. So this talk will be about shattering some of that knowledge. Yeah, so I will explain to you that if you go to a magnetic field, you can actually destroy the Z2 spin liquid, and you can make it a spin liquid with a different gauge structure. Yeah, you get a U1 gauge structure instead. Yeah, and all of this happens only because you're applying a magnetic field, and that's quite remarkable. So let's understand, you know, how we come, you know, to that conclusion. So I said, you know, what we have to do is, you know, we have to put a magnetic field. So this is what we want to study, you know, in the first step now. You take this exactly solvable model, you know, it's a Kitaev model, you put a magnetic field. You put the magnetic field in an arbitrary direction, yeah? So we don't want, you know, to be confined to, you know, one particular direction. So this is really a vector product between, so a scalar product between a magnetic field direction and the spin direction. And, you know, we are doing our numerics, you know, in this case, you're doing a lot of exactization. And the first thing that we can do is we can determine phase diagrams, yeah? Okay, and now because, you know, we do this for arbitrary magnetic field, now I will show you phase diagrams like this, you know, where the magnetic field, I can point in arbitrary directions. So this direction up here is a 1-1-1 direction, okay? And then, you know, so that's perpendicular to the honeycomb plane. Yeah, you know, this is, you know, in the plane. So what you're supposed to see is here, yeah? So here in the very middle here, there's a little dot, yeah? That dot, you know, is a regime in which the original spin liquid, the Kitaev spin liquid, actually is stable. So you're disappointed, yeah? Because, you know, probably you have a very small screen and you don't even see the dot, yeah? So this regime here, yeah? So that's why you want me to do something different. You know, let me change the coupling sign. Yeah, so let's go from a ferromagnetic model, yeah, to an antiferromagnetic one, and then it's easy. Huh? Okay, so now you see the spin liquid, it's big. Yeah, so it's an order of magnitude more, yeah, parameter space, you know, that this guy, you know, occupies. So why is that? Yeah, it's actually very simple to see. The spin-spin correlations are super short-ranged in these Kitaev spin liquids. Yeah, so basically every guy only sees its neighbors, and then, you know, he doesn't care anymore. So if your principal coupling is ferromagnetic, you know, they're parallel. Yeah? And if you put a magnetic field, you will eventually, you can reorient, these parallel spins in the direction of the field, and somehow that destroys, your spin liquid. Yeah. Well, if your principal coupling is antiferromagnetic, you guys are anti-aligned, and then if you apply a magnetic field, well, nothing happens. Yeah. You actually have to flip a spin. Yeah. And that actually costs you a lot. Yeah. So that's a simple reason, why this spin liquid is actually way more stable. Yeah. So so this little blue dot, became this blue range here. And now it didn't slip your attention that there is a second regime here. Yeah. So white, outside here, that's total triviality. But this blue spin liquid here is actually it's surrounded by this brownish blob here, and that's actually what we would like to understand what that is. Yeah. So here's the Kitaev spin liquid. Here's something different. Yeah. So we want to understand these two different phases. Okay. So let's do that. Yeah. Let's take an arbitrary cut now through this phase diagram. So we will go along this red dashed line, which is 5 degrees off the 1-on-1 direction. So on purpose, it's not on some high symmetry line. Yeah. This is how an eigen energy spectrum of such a system looks like. Yeah. So we are going from zero field to finite field. Yeah. So we're going from the exactly soluble Kitaev model, that's this line here on the very left, yeah, to the right. And then you see, that these guys, they move a little bit. Something splits here in the ground state. There's apparently 1, 2, 3 ground states here. Yeah, but really, what happens is, that all kinds of states, come down. Yeah, and here at this transition, hell breaks loose. Yeah, so there's a gazillion states here, yeah, in the middle, and then they start to lift again. Okay, so threefold degenerate ground states here. Yeah, lots of states, here, but it's like a plateau, things don't change dramatically. And then, over here, states, increase linear with field. So here on the right, that's a polarized state. Yeah? So, that's a simple state, that just magnetizes, this magnetic field. Here on the left, yeah, this is the regime where, the Kitaev spin liquid lives in its magnetic field version. Yeah? So once you apply a magnetic field, the spin liquid that you get is a so-called chiral spin liquid. It's a gap spin liquid. Here's a gap. Yeah. So this is a gap. Here are 3 different ground states. Yeah. So what you should have in mind is a gap spin liquid with an edge mode. Okay. So you're saying, well, yeah, how do you see that from your numbers? Okay. Well, what you can do is we can actually take these 3 states and use something that Adrian probably in DMG does all the time now. You can calculate modular matrices. And so that's something very topological. Yeah, that tells you whether something is topological or not. Yeah. So a modular matrix tells you the anion content of your topological quantum field theory. In this case, it should be an Ising TQFT, which has this S matrix, yeah, of universal values. Yeah. And then you can do your calculation. So we do our calculation and we calculate this matrix, and then you see that we almost perfectly recreate those values here. You should appreciate that, yeah, because there's only so many different topological quantum field theories. There's only so many different modular matrices, and they're vastly different. Yeah, so the fact that here's 1/2, a different one here has 3 halves or whatever. Yeah, so it's different values. So we are clearly seeing this matrix in in our numerics here. Yeah. So there's absolutely no doubt, that we have.
How big was your system size?
Yeah. So that's a beautiful question, because our system is ridiculously small. Yeah. So what we are using here is a 24-site cluster. Yeah. Okay. So if you would have asked me, whether we are able to actually pull this off, yeah, calculate this modular matrix from a 24-site cluster, it's actually the guy that you see up here in, this is momentum space, but it's a real space version of that. Yeah. Already for that small system size, you can actually get this number. Yeah, this result. Yeah. We knew that we should get this Ising TQFT, but wasn't clear that actually this type of calculation works. It's a calculation that doesn't work for other famous systems. So the Kagome antiferromagnet, you can try to calculate the modular matrix, it will fail. Yeah? So you see that it fails because it doesn't, give you these universal numbers. You have to get one of the universal number as different TQFTs. Yeah, so this is a cool result. Yeah? So I like it. Okay, so let's talk about this phase in the middle. That's the one that I'm really interested in. Yeah. So the one which has all these states that have come down. Yeah? And first of all, let's ask whether this phase here, whether it's gapped or gapless. Yeah? So let's take a cut out of that phase. Yeah. So we cut here. Yeah. And we look at the spectrum. Yeah. And so we can do different system sizes. They say, oh, they're all small. Yeah. 18, 24, 32. Yeah. And then different geometries at these different colors. And you see, how many states are in this regime. Okay, good. So in 4 per mil, yeah, of the coupling constant, yeah, we have 16 states for a 32-side system. Yeah, this is the smallest finite size gap that we have ever seen. So what does that mean? Yeah? It's smaller than every other system that we know. Yeah. So if you, for instance, take this carbamine antiferromagnet, it's a very famous frustrated magnet that people debate endlessly what kind of state it is. It has a bigger finite size gap than this one. Okay, good. So we're smaller than that. But you can even take a state that we know is gapless. Yeah. So you take an antiferromagnet NaL state, which is a goldstone mode. Yeah. On some bipartite lattice, you diagonalize it. And you will find for the same system sizes, you will find a bigger finite size gap than what we see here. Yeah. So this system clearly is gapless. Aha. So what's happening? So in order to understand that, we looked at the dynamical structure factor. Yeah. So in the absence of a magnetic field, this is what the dynamical structure factor of the Kitaev model looks like. Yeah. So there's a color coding here, yeah. So blue means there's nothing, and red means there's a lot, yeah. So there's a lot of dynamical structure factor up here, and there's clearly a gap. Okay, so there's a gap excitation, yeah, and we know what that is, yeah. So it's the excitation in the gauge regime, yeah. So it's flipping a flux of that Z2 gauge field. It's called a Wison in the language of these spin liquids.
Are the units in terms of K? Units omega?
These, yes.
Okay.
Yeah. So this is the Wison gap, yeah, which is about 1/6 of K. And what's noticeable, and that's also something we know, the Wison has no dynamics. Yeah. The Wison is static. The gauge field is static. That's actually the reason why we can solve this model. Yeah. Because the gauge field doesn't have any fluctuations. It's not mobile. Yeah. And the fact that it doesn't have a dispersion is something that you see here as well. It's flat. Yeah. So every different momentum, you see the same Wison gap. Okay, that's good. Yeah. So now, and because we're looking at the antiferromagnet, it totally drops here at the gamma point. Okay, good. So now we turn on the magnetic field, and what you actually see is that the dynamical structure factor that you have here, it gets smeared out. Yeah, it gets smeared out to lower values. Yeah, but it remains flat. Yeah, so the lower edge here is still flat here. Well, and then here it has come all the way down to 0. Yeah. So what's happening is that this Wison excitation it slowly comes down to 0, and so here it tells you that it comes down at every momentum. So that's why we have so many states that are coming down, because all the momenta see something coming down. So you have a high multiplicity of states coming down. If you go and pick one momentum and look at the dynamical structure factor, yeah, you will see this here more clearly. Yeah, so the original Wison, it comes down, stays low, and then rises up like crazy again. So this is a magnet here on the right. Yeah, that's a magnet of the polarized state. Yeah, so that you see in the dynamical structure factor. Yeah, and here you see how that flux gap, how that Wison gap closes. Yeah. And then in this intermediate regime, it's flat. Yeah, so you don't probably see something going up here, but the most intense mode here remains flat. Let's look at something different. So we discussed before already that we have this double peak structure in the specific heat. So let's look at the specific heat as a function of magnetic field. Yeah. So here in the Kitaev limit, we have this double peak structure, yeah, and in this color coding, yeah, blue low, yellow large, maximum, indicated by point. Okay. So here is this double peak structure, yeah, on a logarithmic scale, yeah, on the order of the Kitaev coupling here, yeah, there's a first peak, a crossover peak, and then here, more intense peak, darker color, is, where the flux ordering, sets in. And now you see that as you turn on the magnetic field, this lower peak, yeah, we can trace it, yeah, it disappears. Yeah, it disappears, below the scale that you can resolve. Yeah, the lowest temperatures here. Yeah, while this crossover peak, doesn't do anything. Yeah, so it just stays where it was. Yeah, and eventually here merges into that, the transition temperature of the polarized state. Okay, so what's happening? Yeah, so how can we make sense of all this? Yeah, so Wison's becoming soft. Yeah? So that's what's happening here at this first transition. Yeah. So here's what's happening. Yeah. So what we think, what's happening is, that there's actually happening is a Higgs transition, yeah, to a gapless U1 spin liquid. So let me explain those words. Yeah. Actually, the best way of understanding that is by not using the language that Kitaev used to solve his models, but a different language where we actually use conventional fermions instead of Majorana fermions, so conventional complex fermions. Yeah. So we can always write our spin operator in terms of complex fermions. That's not forbidden, and we can always do that. Yeah. And Fiona Burnell and Chetan Nayak, some 10 years back, they actually went through the exercise of using this spin decomposition and showing that you can still solve the Kitaev model and understand what the Kitaev spin liquid is in the language of a complex fermion. Yeah. Well, in the language of a complex fermion, the Kitaev spin liquid is a p-wave superconductor. So it's a gapped topological superconductor. Yeah. Yeah. And yeah. So you have a pairing amplitude in that superconductor. Yeah. And what happens, as you in this language now, it's very intuitive actually to understand what happens as you crank up the magnetic field. Yeah. So as you crank up the magnetic field, you undergo a transition to a conventional metal. Yeah. So you go to a system which is gapless Fermi-thermosis. Yeah. So the pairing amplitude comes down. Yeah. Okay. And then over here in the large field regime, you go to a trivial gap insulator. Yeah. So let's write this all in the terms of the gauge field. Yeah. So here in the Kitaev spin liquid, that gapped superconductor, that's where you have a Z2 gauge field. Yeah. While the metal, is a conventional, U1 gauge field. Yeah. So the transition from a metal to a superconductor, yeah, that we know, that's a Higgs transition. Yeah. That's where you take your U1 gauge field and you Higgs it out into a Z2 gauge field. Yeah. And this transition here, to the trivial state, that's actually, where you want to confine that U1 gauge field, but that's actually not allowed in 2 dimensions. Yeah. So that's where you go into triviality. Yeah. So that's, what's happening here on the right. So let's forget about that. Yeah. So what's happening here at this lower magnetic field, yeah, is that you go from the Higgs version to the unhiggsed version of your gauge field. Yeah. So it's the inverse Higgs transition that we all know when we go from a metal to a superconductor. Yeah. You go from the superconductor to the metal. You go from Z2 to U1. So you unhiggs, yeah, your Kitaev model, and you end up in a metal. And if you translate that back into a spin operator, language, it's a gapless spin liquid with a spin on Fermi surface. Yeah. So the idea that such a Higgs transition between U1 and Z2 spin liquids might exist and might happen is something that some of your Boston colleagues, Max Wedlitsky, Senthil, and Subir, have been musing about some time ago, but totally out of the context of a microscopic model. Yeah. So the astonishing thing is that one of the models that we all know, yeah, and is so well studied, the Kitaev model, actually exhibits this physics. Yeah. And we simply didn't look at this, 10 years ago when we first studied, magnetic field effects in Kitaev models. Yeah. So I actually did some of this at Station Q 10 years ago, and we didn't look at antiferromagnetic models for some reason. We should have. Let me tell you about the stability of that U1 spin liquid. It's actually very stable. Yeah. So now, if you add all kinds of other terms, Heisenberg terms, this gamma term that's also in the microscopic description, always here at zero perturbation, you have that Kitaev spin liquid, and on that, in the magnetic field is this gapless spin liquid. Yeah. So now, as you vary parameters, so these and then field directions, what you see is that this phase, this gapless phase, is always there. Yeah. It always piggybacks. It always sits on top of this Kitaev spin liquid. Yeah. So it actually looks like the generic thing to happen. So you get this gapless spin liquid, and at low field, you actually Higgs it out into the well-known Kitaev spin liquid. Yeah. So so that's something to remember for the next session. So our work, led others to think in more analytical terms about, how spin-on Fermi surfaces, look like. So Yin-Chen, wrote very nicely, how these spin-on Fermi systems looks like, from projective symmetry analysis, and what actually happens as you go through this phase. Yeah. So this Higgs transition is where you end up in that spin liquid, and you have a finite spin-on Fermi system right away. Yeah. And then as you traverse this phase in the middle here, actually, what happens is that the Fermi surface shrinks, and then exactly at this point is where you get down to zero Fermi surface, and that's where you get out. Yeah. So let's go back to ruthenium trichloride and ask how relevant any of this here actually is. Yeah. So it turns out that getting the microscopic parameters for ruthenium trichloride, consistent, yeah, across, different, people running up initial calculations is not trivial. And, there's only slowly consensus, of how to, do this, and then, discuss, magnetic field effects. So Hae-Yong, managed to, cook up, a version of a model that actually, allows you to go from a zigzag ordered, phase in the magnetic field to a Kitaev spin liquid, which is a non-trivial feat to accomplish. Yeah. Other people like Jose Valenti, yeah, they have very carefully gone through their ab initio calculation, and when they place alpha ruthenium thyroid in their phase diagrams, they always end up as a ferromagnetic Kitaev couple. Yeah. So that might sound like a disappointment, because for what I wanted to do, this U1 story, I needed that antiferromagnetic coupling. But it turns out that by virtue of some dualities that are inherently in all these phase diagrams of various couplings, Heisenberg Kitaev couplings, it turns out that a antiferromagnetic Kitaev through that duality is not that far away from what they actually discussed. Yeah. So for us, it's an open question, whether ruthenium trichloride, this system, which seems to realize, the Z2 spin liquid, yeah, the one that actually, has this chiral edge mode, that we see in the Summer Hall effect, whether it actually is, the Higgs version of a U1 spin liquid. Yeah. So, so that's something we muse about, whether that is actually the way that we should think about that system. Yeah. How would we see that? Yeah. Let's come back to this idea of this new quantum Hall effect, that is seen in ruthenium trichloride. Yeah. So the observation, of this half quantized plateau, yeah, again, is super sensational. Yeah. So it tells you, yeah, that you have Majorana modes. Actually, in 2018, there were 2 experiments being done that were very similar in their result. They saw this half quantization. Yeah. So this experiment was done that I showed to you was ruthenium trichloride. At the same time, Moti Heidblum's group at the Weizmann, looked at the 2-dimensional electron gas. Yeah, so a typical fraction quantum Hall state, so the 5-half fraction quantum Hall state, and also showed that that system, has a half quantized thermal conductance on the edge. Yeah, so seemingly very similar results. Yeah, half quantization. Majorana fermion edge modes. Yeah, but actually in very different systems. Yeah. So the fraction quantum Hall state is, what I explained in the beginning. That's a state which has a bulk gap and then an edge mode. Yeah. But actually, this Kitaev system, it doesn't have a bulk gap because it's a bulk material, and in the bulk material there's always phonons, and phonons are always gapless. Yeah, acoustic phonons are always gapless. Yeah, so this system is actually not gapped. Yeah, so there's phonon modes that you can couple to that should actually destroy all quantization. Yeah, so you would think that cannot happen. Yeah, so you have a gapless bulk. Yeah, and then if you have a quantized edge mode, you would think that the quantized edge mode, yeah, couples into the bulk, and all quantization goes away. Yeah, and actually, so my colleague here in Cologne, Achim Rosch, yeah, simultaneously, Leon and Santa Barbara, they actually understood, in very different calculations, why this doesn't happen. Yeah? So Achim went through a beautiful discussion of quantum anomalies to explain that the edge mode actually cannot leak into the bulk. Yeah, so it just doesn't happen. Yeah, and that's actually why you see quantization in the presence of gapless bulk modes. Yeah, so a very different Hall effect from all other Hall effects which are gapped in the bulk. Yeah, so phonons are still needed. Yeah, so we need those phonons to actually couple heat to the system. Yeah, and that's also the reason why we can only see that quantization effect at finite temperatures. Yeah, so if you go to too low of a temperature, we will freeze out all phonons. Yeah, and then there will be no heat carrying at all. Yeah, so we will not be able to couple to the Majorana fermion. Yeah, so at ultra low temperatures, we would expect to see that Hall effect disappear. Yeah. Good. Let me very briefly mention, because I think I should be at the end of my time, that there's one cool experiment that has been done by the Matsuda group by discussing with us, and that is the observation of an anomalous, thermal Hall effect. So, so you might think, that you need a perpendicular field, yeah, to drive, the thermal Hall effect, yeah, because that's, what we learned, in the electronic case. But actually, for this version here, yeah, it's not true that we need it, because the Hall effect that we have in this system is not, by the virtue of formation of Landau levels, yeah. But we are talking about, a chiral spin liquid. It's topological non-trivial bands with a Chern number, that we are dealing with. Yeah, that's a very different scenario. Yeah, so that's what Haldane actually worked out. Yeah, yeah. So we have a system like that, and that actually means that we can observe a quantized Hall effect not only for a magnetic field that's perpendicular to the sample, but also one where we tilt all the way up to in plane. Yeah, and when you do this, yeah, you will actually see that the Chern number switches sign a couple of times as you rotate your magnetic field, but it's still an integer Chern number even for the in plane field. Yeah, this some of these different angles Matsuda actually measured and saw exactly this flipping of the Chern number, in particular also for the in-plane case, which is experimentally particularly relevant because the out-of-plane field generates a huge magnetic torque and breaks samples, so that goes away by virtue of having an in-plane field. Okay, good. So what's next? Let me close on that. Yeah. So something that we worked out earlier this year is there's also spin-1 materials that have Kitaev interactions. That's something that Haeyong Kee's group in Toronto beautifully showed. And then Curran went through basically the entire calculation again and showed that if you consider spin-1 Kitaev models and in a magnetic field, you will basically find exactly the same signatures as for the spin-1 half version. Yeah, so you will also find this U1 spin liquid in those materials. But what's interesting is that a spin-1 Kitaev material has generically antiferromagnetic interactions as opposed to a spin-1 half Kitaev material, which seems to have in all the known versions of a material that we know ferromagnetic interactions. Yeah. So we hope that some of these materials will attract our experimentalists' attention and be studied. So let me come to the end. So what I tried to explain and discuss today was that the Kitaev spin liquid story that we know is a textbook example of a Z2 spin liquid. But in a magnetic field, everything changes, and you can get this Higgs transition to a U1 spin liquid, a gapless spin liquid, which we actually think of as a parent phase now of this conventional chiral Z2 spin liquid. Yeah, And it should actually have its signature also in these quantum Hall experiments. Yeah. So which is very different from the Sommer effect. Let me acknowledge one last time, Kieran, for his great work on this project. So thank you. And now, please ask questions.
Thank you, Simon, for a beautiful talk. And now it's time for questions. Please feel free to raise your hand or unmute yourself.
I would like to ask a question, Viktor Yakovenko. So the question is, why this magnetic field that promotes transition, this Higgs transition from Z2 to U1? I mean, I understand there could be, Higgs transition, but why magnetic field specifically controls it? I mean, what's the mechanism?
Yeah. So, well, so I showed you.
Hablar, venían los gritos. ¿Dónde está mi head?
So it softens the visors. Yeah. So why does no other interaction do it in the same way? Well, so for that, you might want to recall the following. So the Wison, in the Kitaev liquid in a magnetic field, actually bounds a Majorana zero mode. So it's a fermion, and by being a fermion, you actually prohibit it from doing the most simple thing, and that is condense, in a Bose-Einstein constant, which is a one version of saying what happens if you put, for instance, a Heisenberg interaction on the Kitaev model. In the absence of a magnetic field, the Wison is a boson, and the Heisenberg interaction has the effect that the Wison becomes dynamic, so it gets a dispersion. Eventually, it becomes soft, it condenses, and it uses zigzag magnetic order. So that's boring, So I think the magnetic field is relevant in that sense, that it ensures that your Wison is actually a fermion, and then when it becomes soft, it has to do something different than pairing up, and it forms a metal. For us, the question that we pursued for a while was asking whether other things can do the reverse, go from the U1 to the Z2, so induce a Higgs transition. So instead of lowering the magnetic field, can we do other things? So we played with Jakuzinski-Maria interactions and such things, asking whether they can have the same effect of Higgsing, back to the Z2. But we didn't manage, so we never found anything else but the magnetic field doing this trick.
Very good. Any other questions?
Okay. Can I ask you a question?
Sure.
Yeah. Hi, Simon. This is Mehdi Kargarian. So my question is about spin-1 Kitaev model that you mentioned. Is it also exactly solvable like the spin-half Kitaev model in terms of Majorana?
Yeah. And so while I said in oops, let's go the other way around. That's the wrong direction. Let me show my screen again. That we can find that U1 spin liquid also in that case. So I don't find my cursor. Here it is. Let's go back. Yeah. So there's also the U1 spin liquid here. Yeah. What we actually do not know, what's happening over here. Yeah. So is he low field phase, the same non-abelian phase as in the spin-1 half case. So in this case, we haven't managed to calculate that modular matrix, and pull the same trick, to say exactly what's happening here. So there's a possibility that this is a slightly different phase, and we don't know. So there's no exact solution. So we
Thank
don't
you.
know.
Can I have a question if I may?
Sure.
Hi.
Go ahead.
Well, in fact, two, if I could. One is that the Kitaev model introduces a magnetic field by a different kind of interaction, which of course is exactly solvable still. So physically, of course, it's a different interaction, but I don't know whether people have seen, look at like this plot you have here on the screen at the spectral function as a function of that interaction.
Yeah. So what you're referring to is that if you point your magnetic field along the 1-by-1 direction, you can Kitaev's original paper already has an argument that by perturbative treatment, you get what's called a kappa term. It's basically a next nearest neighbor hopping of the Majorana fermions. Will mimic the effect of the magnetic field, and that is true. Yeah, but it only does so for the small field limit. Yeah. So you will actually never go, when you turn on the, this additional election, this kappa term, yeah, you will actually never go to the polarized state, yeah. So you're bound to stay in this phase, yeah. So you will never see this intermediate regime, yeah, because that's just not in that calculation, yeah. So
only because it is perturbative.
Yeah, so you would have to do a higher order perturbation theory and then see what whether you have a chance to see some higher order term that does a job of what the real magnetic field does, yeah. Okay. So I'm not aware of anyone doing that.
Right. Okay. And my second question had more to do with the ruthenium trichloride. You made the argument that by symmetry that is very close to the antiferromagnetic, but the deviation from it will presumably have consequences on, say, the quantization of the thermal Hall.
Yes. Yeah.
Can those be quantified or?
Yeah. So the question is actually in the thermal Hall experiments. Yeah. So where would we expect to see the U1 spin liquid here? Yeah. So by the same logic, that I applied here is, you would actually see it between the Z2 spin liquid, yeah, and the in the polarized phase at high magnetic field. So it would be interesting to zoom super into the higher field transition, where the quantization breaks down, yeah, to see actually where you see some spike, in the thermal transport, that indicates that you're actually having a different spin liquid for a small region there, where you have the U1 instead of the Z2. Yeah, experiments are super tricky in the magnetic field. Yeah, so it's not done very fast, and it's only one group which has accomplished this so far. So yeah, let's wait.
Okay, thank you very much.
So Simon, it's Oleg Starek here. Is it your argument specific to 2 dimensions? What about 3-dimensional liquids?
Yeah. So we have done a lot of work, looking at 3-dimensional Kitaev models, with Maria Hermanns, as you might know. So 3 dimensions is different, and actually we know this before we start. Yeah. So we know that our system is a free Majorana system in the Kitaev language, and it's a Majorana fermion system, which means it has particle-hole symmetry. And then depending on whether we have a magnetic field or not, we have time reversal symmetry. Yeah. So that puts us in the pure Kitaev model, in the symmetry class BD1, and in the magnetic field case in symmetry class D. So now we can actually go back to Altan and Simbao, look up their the Kitaev-Ludwig classification of topological insulators by these symmetry classes, and then it's important to note that dimension is also relevant. Yeah, so it turns out that 2 dimension and 3 dimension are different, of course. Yeah, there are different columns in that classification. And so what's interested us, is here is, so we are in class D because we have a magnetic field, yeah, so we break time reversal symmetry, so we only have particle-hole symmetry. So the non-trivial topological insulator is only there in 2 dimensions, yeah. So the Z2 spin liquid, so the chiral spin liquid, yeah, so there is no one-to-one correspondent of that in 3 dimensions. So why did we do 3 dimensions? Well, if you go in 3 dimensions, what you get, what's richer there is that instead of having this direct dispersion for the Majorana fermions, you can get all kinds of other nodal structures for the fermions. You can get Majorana Fermi surfaces, wild Fermi surfaces, nodal lines, and actually the wild Fermi surface, the wild nodes, yeah, is actually the example. So instead of getting a topological insulator, yeah, you can get a topological semi-metal. That's actually what you get. Yeah, so a magnetic field will give you, something like that, for instance. Yeah, but it will never give you, this version. And well, where there is no Higgs version of a Z2 spin liquid, there's also no un-Higgs version. So yeah, but of course, the Majorana Fermi surface spin liquid is a cousin, of this guy, which is this U1 guy, has a spin-on Fermi surface. Yeah, so it's really a spin-on with a Z quantum number. Well, the other one is just the Majorana fermion. Mm-hmm. Both have specific heat, which is linear in temperature. Yeah, so very remarkable states. Yeah, so they look like metals.
Mm-hmm. Yeah, thanks. And maybe if just very short on in your calculations. So can you also look on central charge for that intermediate region? So do you see that it's shooting up, or you know, if it's
so central charge is tricky, yeah. So you know, so the generalization is this modular matrix, yeah. So but you know, the modular matrix we could calculate, you know, in the middle of that phase, you know, where the gap is, you know, nice and finite, yeah. It's nothing that you can easily calculate, you know, all the way up to the edge and then, you know, say, oh, you know, and here it changes, yeah, in such a way. So so no, so we haven't managed to see that. We also haven't managed to, you know, visualize, you know, the spin on Fermi surface for that. You know, our system sizes are way too small. Yeah, so you need much larger sizes to have the resolution in K space to see that. Other questions?
Any other questions? No more questions from
I have a question.
Yes, please go ahead.
So earlier in the talk, when you talked about how you had that gap spin liquid phase, that's always like piggybacking the Kitaev spin liquid phase. It looked in when you're showing the field dependence of those phases, it looked like for 30 degrees, you don't have that gap spin liquid phase. Is there a reason for that?
No, there's there's no particular reason for that. Let me show you that. So you're referring to the fact that, you know, here there's a region where it doesn't happen, yeah?
Yeah.
No, so there's, you know, there's no particular reason why that is the case. Yeah. So yeah, so this, you know, the entire shape is you know, is very ungeneric. Yeah. Yeah. So to some extent, this is boring, yeah, because you do not get the intermediate phase. Yeah.
Yeah.
Which means that, you know, if you're now interested in writing down field series and these types of things for phase transition, you know, that is a different problem than the one here, but that's a different type of work.
Okay.
All right. Any other questions? Well, if not, let's thank Simon one more time. Thank you, Simon, for staying late and going to your office this time in the evening
Thanks for having me.
to join us. It's a pleasure to have you with us. And thank you all for joining. And we thank the speaker one more time. And we meet you again next week for the last seminar of the semester, of the year.
Thanks.
Thank you all. Goodbye.
Thank you.